I'll give 30 seconds and then I introduce Rafael. Okay, so it seems that the YouTube channel is now running. I can now proceed with the third keynote of the conference. So good morning, good afternoon to everyone. So welcome to the third and last day of CIoT 2020. And we are really pleased to welcome Raffaele Bruno. So Raffaele is a researcher with the National Research Council of Italy and a member of the Ubiquitous Internet Lab of the CNR, Institute of Informatics and Telematics in Pisa. So Raffaele is really well known worldwide for a number of contributions in several areas related to the ubiquitous internet, and more recently with a number of original and striking contributions on IoT protocols and architectures, edge computing, 5G, vehicular networking, and green networking as well. So Raffaele, thank you really on behalf of the audience of CIoT 2020. Thank you for sharing with us your experience and your knowledge on the topic that we are going to address today on urban sensing. As I announced yesterday, this will be a great complement to other keynotes and talks that we had during the week. So Raffaele, thank you again, and the floor is yours. Thanks, and good keynote to all of us.
Thank you very much, Marcelo, for your very kind introductions. And let me also thank again you and the organizers for inviting me to deliver this keynote at the conference. Okay, the title of my keynote is Urban Sensing, the role of IoT, edge computing, and distributed analytics. What I would like to discuss today is basically how edge computing, and more in general, data management at the edge of the network, is transforming the reference architectures of IoT ecosystem, and which is the impact in terms of research challenges and opportunities that this is generating. This talk is the result of the contribution from many colleagues, and here you can find a very incomplete list of the contributors to this talk. So the agenda of my talk is the following. I would like to set up the context of this work by starting from a use case. And this use case is actually urban sensing and computing in a smart city scenario. Then I will start elaborating a little bit more on which are, in my view, the trends, the bottlenecks, the trade-offs that are currently transforming the reference architecture of IoT systems from what we have known in the past years. And in particular, I will discuss the role of data gravity in these transformations. And then I will move to share with you my view, which is obviously not only my view, of what kind of edge platforms we need in the case of an IoT applications. And in particular, I will try to discuss what I mean with the smart edge, and what are the typical functionalities that we need beyond simple computation offloading. And I will discuss the research challenges of this vision by providing you some examples of research activities that have been conducted in my research group in the past couple of years. So let's start by setting up the context. So we know that people are living in cities, and the populations is moving from the countryside to the cities, and we expect that 60% of the global population will be living in cities by 2030. And also we have this phenomenon of the mega cities, so huge urban agglomerations where people are living and there are more than 10 million inhabitants. In Brazil, I know that there are at least 2 of these megacities nowadays, but by 2030 there will be almost 40 of them in the world. And big cities comes with big challenges in terms of traffic congestions, in terms of air pollution. So yesterday we had this wonderful keynote explaining on how difficult it is to build some sustainable, long-term and precise air quality monitoring systems. But we have other challenges related to energy supply, for instance, waste management, social inclusions. Now, how these big cities are trying to tackle these challenges? Basically, the approach, the common approach, is to deploy smart city solutions. So what is a smart city? Smart city is basically nothing else than an urban area that is embedded with different types of IoT devices. These IoT devices can be sensors mounted in the different infrastructure of the cities, can be sensors on wearables and personal devices, can be sensors deployed on moving vehicles. And these sensors are basically used to collect heterogeneous data from different, characterize different aspects of the cities. Then all this raw data is processed, elaborated, and from this raw data we can infer some insight on how the different infrastructure and services of the cities are used. And we can basically build some intelligent decisions, support systems in order to manage these resources and services in a more efficient way. So to some extent, the smart cities is nothing else than an examples of a typical cyber physical system. So where we have basically the physical world, where we have monitoring sensing that is providing data to the cyber physical world, where we have elaborations, and then we define the feedback that goes back to the physical world. But how to build such a smart city systems? The typical approach is a 4-tier architecture, so where we basically have a sensing layer that is comprising everything related to the sensing. Then we have the connectivity layer, where basically we have the communication technologies and also the different modalities with which we can collect the data. And then we have the data layer. So in the data layer, we have all the data management functionality, so the storage of data, the analysis of data, and this is all this data that's then used on the service layer to provide the services to the users. Now, in my talk, what I would like to focus on is on this data layer, but from a networking perspective, as I will clarify in a few slides. So if we have to build this kind of architecture, the typical reference model that we have been seeing in the past years was the following one. Basically, we have this swarm of sensory things that are providing this data. These sensors are connected to a gateway that providing transparent connectivity to the core networks, and this data is then moved to some very remote cloud platforms. Because in this model, the focus is on data elaboration services, and there is a big market for cloud service providers because there are huge requirements for storage of this massive amount of data. There is interoperability issues between heterogeneous devices. There is the need to have some centralized decision support systems. And indeed, what we have seen is that in this model, things are just a service. So there is the virtualizations of the physical things inside the cloud. And this is then these virtual objects are basically composed and used by the applications. So this has been a very, very successful model for building IoT solutions. And indeed, if we look to the landscape of IoT platforms, where platforms can be anything from a solution for device management, for connectivity, for interoperability, for service development and deployment. And if we look to the plethora of platforms that we have, most of them are cloud-based platforms. And there are very successful stories here. All the big players in the cloud market are their own solutions that are selling to their customers. But new trends are emerging, things are changing quite fast. And today I think that there is a quite common understanding and agreement, at least in the research community, but also in an industry environment, that we are migrating towards a different model. This different models is a model where we basically have a continuum of resources between the devices and the cloud, and the remote cloud. This is creating a sort of hierarchy of different types of resources, not only computing power, but also memory and network services and control services that are used to collect, aggregate, and process data. And basically, what is really fueling this and driving these transformations is the role of data and the role of data management. And try to motivate and explain this, I would like to use an analogy that's quite famous. It's called the data pendulum. So the idea of this is that the data has a gravity. And this is the center's gravity is not stable, it's moving because it's subject to different forces. These forces can move the data gravity towards the core, so towards the centralized workloads, or towards the edge, so towards the distributed processing. And this basically today we still have forces that are pushing the data in the opposite directions. And just to mention, there's, for instance, still trends that are pushing the data towards the cloud. Just to give you two examples. If you look to the energy efficiency of current wireless technologies for machine-to-machine, machine-type communications, we can see that there are technologies that allows you to spend 1 microjoule to transfer 1 bit of information. So depending on the hardware of IoT device, it might be more energy efficient to transfer the data rather to process the data locally. The second trend is the complexity of the applications. It's true that the hardware, the IoT devices are becoming more powerful, but it's also true that applications are becoming more complex. If you just look to, for instance, the typical models of deep neural networks that are used in some popular applications, and we compare these models in terms of number of operations, in terms of number of features that they need to process, we will see that there is a huge increase in computational complexity and in size of this model. So these are trends that will justify to move the data and the processing of the data to the cloud. But on the opposite side, we have many more trends that are pushing towards the edge. And I'll give you 3 examples. The first examples are related to network performance. This is true that the bandwidth is increasing. If you look to the compound annual growth rate of bandwidth worldwide, it's increased by 22% in the last years, but that data volume is increasing much faster. So the more bandwidth we have, the more capacity we have in the networks, and the more data we are generating. And not only the data is increasing, but also there is an exponential increase on the number of connections. And these connections are merely connections related to IoT devices. The other trend is related to the new use cases for IoT applications. There are many new use cases related with the latency critical, latency sensitive applications, like, for instance, real-time control of machines, industrial automations, autonomous driving, where we really need a few milliseconds of delay between the data generations and the feedback that we get from this data. And so what we need is to have a data processing that is proximal to the data producers. Then there are some trends related to the business, because it's clear that the big cloud providers have dominated the market, although they are now understanding that they should extend their centralized cloud service with the more distributed capabilities. Let's think, for instance, to Amazon with the Green Grass initiative launched in 2016. But also the tech operators are now seeing a big opportunity for a novel market for them. So, and we have witnessed the new architectures and new technical standards like the MEC that are basically allowing access networks to host cloud computing capabilities. And so the idea that a telco might basically behave as a local cloud provider and to provide in as a service manner distributed compute and storage capabilities, or a platform for developing application on the edge infrastructure. So this is pushing the deployment of more edge computing in the networks. And then we have also some consideration about data ownership and data privacy. For instance, there is a lack of trust in global cloud platforms. that is in addition, there is concerns on the relevance of data, of moving all the data in a single place. So most of the data is relevant only locally for some very local decisions. So the scope of the data is local. There is no reason to move all this data to a remote place. And there are also some regulations forces. For instance, in Europe, we have the General Data Protection Regulations that are basically allowing users to have full control of their own personal data, and they are introducing accountability for the data usage. So the users must know who is using the data, who is storing the data, who is transferring the data towards a third party. And there is this introduction of the personal information management systems, where you have basically the possibility to define your own access policy for your own data, and where to deploy these personal information management systems. It's possible clear to have a cloud-based solutions, but now we are moving again to decentralized teams model. So where you have sort of a data box that is your own personal data box that is very close to you. So in summary, all these are explaining why the edge is becoming so relevant, so important also for the IoT domain. But what I would like to discuss now with you is that what we are aiming for is not another computation offloading platform, because what we are needing is really something more, something different. Because what we have is that we have multiple sensor data streams, and these multiple sensor data streams that are going to serve multiple IoT services. And we need some functionalities to have these smart orchestrations of these IoT resources at the edge of the network. So my claim is that edge for the IoT will not be a simple computational floating platform. And I will give you 3 facts that justify my claim. The first fact is that we are witnessing a significant diversification and customization of sensors. There were huge heterogeneity in terms of type of data, sampling interval, accuracy, and the range of the sensors. But what's very important, the same object in the same space is now monitored by many, many sensors. Let's think to a car, to your apartment, to a smartwatch for monitoring physiological parameters. So this is posing new requirements for the edge, because what we have to implement inside the edge are functionalities to have these multimodal data function aggregations to support the heterogeneous quality of service requirements of the applications, to be able to activate the best sensing resources on each IoT device. Because now in IoT devices, the full car and the entire home can be considered as an IoT device with multiple sensors. But even more importantly, if IoT applications are basically different requirements in terms of the source of data that they are processing. Just let's think, for instance, to augmented reality applications. We are used to think to our smartphone that is taking videos, pictures, and then these pictures are sent to some remote service where they are processed and then augmented with some additional layer and sent back to you. Just your own data, one stream of data. But let's think to a surveillance service and see. We might have multiple cameras that are basically monitoring the same scene, that have partial views of the scene. Then you can augment this information, the visual information, with the microphones that are collecting audio signal, that are helping the service to detect and understand what's happening in the scene. So what we have is a single service that is basically requiring the collections of multiple data streams from these spatial dispersed devices. So what is important is to have some orchestrations of these data streams within the edge. For instance, taking into account which is the data dependencies between the data producers and the data consumers. For instance, to minimize which is the flow of traffic that is needed to be transmitted within the edge. So traffic orchestrations to minimize data redundancies between services with overlapping spatial scope. And the third fact is that we are used to think about cloud resources as isolated and dedicated resources. You have your own virtual machines in the clouds, and it's just yours. But in the IoT domain, there are many situations where you have to think to shareable resources. For instance, we are interested in similar data, so why not to use data caches to facilitate information reuse between services? Also, you might share the same code, for instance, libraries for video analytics. So you have to think about service provisioning in the edge with shareable resources. And so this leads to what I'm calling to a smart edge. So basically, a smart edge is an enabler. It's enablers of brokering, of matchmaking capabilities between shared sensor data stream and shared IoT service. What we can imagine is basically that we have users, and users can be a municipality, can be a police department, it can be a school, it can be a single citizen, and these users are asking services to a provider with a catalog of different IoT applications, and these IoT services are instantiated on a platform running on edge resources. And this platform needs many functionalities to manage in an efficient way the data that is generated by the billions of IoT devices that have to manage. We need a traffic shaper in order to shape the traffic from the sensors that are activated. We need the quality of service aggregators that are able to aggregate quality of service requirements from different applications that are interested in data from the same regions. So with overlapping geographical scope, we need IoT orchestrators that are able to trigger IoT devices to orchestrate, coordinate IoT resources, to monitor the traffic, to route the traffic within the edge networks. And we need resource caches, for instance, to support information sharing and to control data redundancy. So what I think that there are a lot of research opportunities for building these new capabilities for edge platforms. And what I would like to do in the following 20 minutes is basically to show you some research examples of activities that we have been carrying out in my research group by myself and by my colleagues on these different aspects. So the first topic I would like to discuss with you is how to provide sensor data streams with the capability of self-regulating their data rates. And we basically contextualize this work in the case of REST-based architectures. So for data streams that are basically managed through COP-based connections. So what is COP? I think that all of you know COP as a web transfer protocol that is more or less an HTTP protocol adjusted and adapted for resource-constrained devices. But COP also provides many additional features with respect to HTTP, like, for instance, the possibility to have to control the transmission rate of connections. Specifically in COP, what you have endpoints, and these endpoints exchange messages. These messages are exchanged through transactions, and you can regulate the rate of your transactions. But the flow control that's implemented in COP has many shortcomings because it's very basic loss-based congestion control. Basically, COP adopts a stop-and-wait approach for flow control. There is there is a lot of instabilities in the congestion control mechanisms of COP. It's not resilient to bursty traffic or not non-responsive traffic like UDP, and also can suffer significant degradations when there are sudden changes in network conditions. So what we've done is basically to try to enhance the flow control in COP. And in this work, it was published in WOMAN 2018, we basically proposed to have a sort of network-assisted congestion control, also augmented with the rate-based flow control. What I mean, basically, let's consider the classical network of the sensor systems where we have our sensors or IoT devices that are connected through multi-hop wireless path to a gateway, to a border router, to an edge node. So this, when we activate the sensors in the networks, these sensors will produce the data stream. These data streams have to share some bottleneck link with other streams and networks. So our idea is to use a collaborative approach for estimating which are the bottlenecks that are in the networks. So basically, each node locally make some estimate on the which is the service, the capacity of the links towards parent node. We have a possibility to distinguish between estimators that compute basically variability of the measurements in the short term, or estimators that are computing the average behaviors in the long terms. And then we basically combine this local estimate as the informations are sent towards the gateway. And the gateway receives all these all the measurements from the different nodes, and then sends back to the source an estimate, a refined estimate, which is the bottleneck that we can have on the different regions of the network. So, for instance, we have this subtree, and this is the capacity of the links. This is the bottleneck. If we consider this region of the networks, then the bottleneck will be this could be this link here. And so basically what we do, each root of each subtree applies some sort of max-min fair rate allocations to the child nodes. And this allocation basically continues as the rate information is sent back to the source of the nodes. And in the end, basically, the rate located is used to adapt the rate using a multiple increase and multiple decrease scheme. We basically evaluate, we have a prototype of this COP variant. We evaluated this prototype in an emulation environment, and we basically focus on a case where the traffic burst. Because what we are interested is not to consider the simple temperature readings, so a few bytes information, but let's think to a high quality image. So you need multiple messages to deliver the full information. And when the service, latency sensitive services, is not interested to the average delay per message, but it needs to know how much time it will need to recover the full image, to receive all the images. Basically, what we were able to achieve with this proposal was to reduce the dispersion of the data collection delays. So we reduce the time needed to transmit a bunch of messages in the network. However, this is in basically a solution that requires the collaboration of the nodes in the network. So it's breaking the end-to-end principle of typical flow control mechanisms. So we decided to also investigate an alternative approach where we basically keep the end-to-end estimates, but we abandon the loss-based approach for congestion control, and we try to adopt a delay-based approach for congestion control. So basically, which are the advantages of using delay-based approaches? Basically, that they are able to detect the onset of congestions before the congestion really appears. So they are able to adjust transmission rate before congestion, and that tends to prevent the increase of queuing delays. That is very important in situations where latency is the key concern for the application. The problem is that it might be difficult to get a reliable estimate of delays in the networks, and they are showing generally poor performance when delay measurements are noisy. So again, the key basically contributions of this work was try to define reliable ways to estimate delays in IoT environment. And we propose an hybrid approach where we basically combine measurement of packet loss ratio and measurement on delay variability. So this measurement delay variability are used to basically define characteristic regions of the networks. And then we decide to be basically the rate adaptation policy based on which region we are. For giving you examples, if we have observing a very high variability and no negligible packet losses, so it's reasonable to perform a rate decrease, but in a very aggressive manner, because we might be in a situation where there is degradations of the network conditions and congestion. But if we observe high variability in the delay, but the packet losses are negligible, then we might better to do a slow rate decrease because maybe the network is not congested. And so we have, again, also a prototype of these solutions, and we evaluate comparing the solution with the other basically standard COP and some other more recent enhancement of COP congestion control products are called COCOA. And what we observed that comparing with UDP traffic, so basically with traffic that's not flow controlled, what we observe is that when the load of UDP traffic is increasing in the networks, the throughput obtained by the backup significantly degrades, while with our solutions we are able to provide a much more robustness against this non-flow controlled traffic. One limitation of this approach is basically that we are relying on round trip times. That is providing a partial view of the networks. It's just one measurement. So basically we were trying to see if we can find a representation of the network state that is, let's say, more complete, provides richer information. And we were inspired by the huge work that there is ongoing in the internet research community about flow control in the internet. And there are many, many different approaches. And in particular, we were interested in looking to the BBR approach. So BBR is a rate-based congestion control. So this is what we are looking for. And the idea of BBR is basically to try to limit the number of packets that are in flight in the networks to the value of the bandwidth delay product. Why this? Basically, if just we look to this very simplified representation of what happens to a classical connections in the networks that is sharing a bottleneck, we see that when the traffic, the amount of traffic in the networks is low, basically the round trip times are stable and your throughput is increasing. At some point in time, when you inject too much traffic in the networks, you need to queue the traffic. And so queuing the traffic, you increase the delay, but this is not causing you a decrease on the delivery rate. At some point in time, you are filling your queues and then you start losing packets. Now, classical TCP is working on this point, while what we want to do is to try to work on this point where we have minimum delay and maximum delivery rate. And this is what BBR is designed for. Then it's introducing some additional mechanisms to have the probing on the networks in order to understand if we can increase or decrease the rate, if the network condition changing. So what we've done is to basically get inspired by the BBR and to try to implement the BBR principles within COP. And again, the problem is, as usual, is how we estimated this bottleneck capacity. Because in BBR is just the maximum throughput in a time window, but there are such significant dispersion values in a typical IoT environment that we basically came up with an alternative approach where we have a weighted sum of both the maximum and the minimum throughput that is measured. And the weight we gave to these two measurements depends on the level of packet loss that we are also measuring the network. Basically, what we were able with the BBR was not only to reduce the probability of retransmitting packets as with respect to the standard COP, but most importantly, what we were able was to significantly increase the fairness properties of COP. While in basically the classical COP shows a very poor fairness in the network. So this is giving you a few examples of how important it is to basically still working on these self-rate regulations on data streams, because there are still huge problems with the fairness, with the robustness of, and also with the very delay variability on the data streaming or the data streaming process. The second topic that I want to present to you is the activities that have been done recently on the design of data brokering services jointly with the resource allocations at the edge of the network. So what I mean with the data brokers in this context? For me, let's assume this scenario where you have this IoT domain. So each IoT domain has its own broker, and then we have applications that are accessing the physical resources. So the broker is the entity that is regulating the access to the physical resources and respond to the service requests from applications. So a broker should basically host multiple different services. One is the resource directory service to allow the applications to basically discover which are the resources that are available in the IoT domain. And also what we basically imagine is that the broker should have some observing capability. So what is an observing? An observing is an entity that allows the broker to probe the physical resources and to collect data and to keep that in a local cache. This local cache is used to satisfy the service request coming from the application in a more efficient way. So basically, the broker acts as a mediator between a competing application that may request a similar sense of data, decoupling the application requirements from the capabilities of physical things. So first of all, we started from a very practical problem. So we were saying, let's do some engineering work. Let's try to design our very simple, practical broker. So what we imagine is basically to have a system where the applications are clients that are periodically issuing requests for data updates to servers that are basically are sensors that are deployed in the network. And in between, we have this broker that is basically empowered by COP, because in COP there are some very interesting functionalities that are defined. In particular, there is the reverse proxy functionalities that enables to have these intermediary entities that are able to respond to requests from clients on behalf of one or more COP servers. So what we are trying to do is to develop a system so that in a simple system where you can decide, the broker can decide which is the probing rate of to basically ask updates from the COP servers in order to be able to satisfy as much as possible the requirements from the application without congesting the network. And our idea is that we are working in a very challenged environment, like, for instance, in a factory, so in industrial scenarios, where there is a lot of unreliability in the communications. So basically, what we're trying to do is to try to get a balance between the needs of having a reliable communications with also the needs to avoid congesting the networks and being able to satisfy the quality of service requirement of the application. So we leverage the work that we have been doing on the congestion control for COP. And basically, we are here measuring which is the reliability at the application layer. So we measure what we call the transaction loss ratio. We're not interested in understanding at the link layer, which is the capacity. We want really to understand how many transactions are lost during the communications between the COP servers and the brokers. And we basically, based on the reliability degree that we measured on the communication path between the broker and the COP service, we basically adjust our probing rate. We have conducted both simulations and real experiment. Just want to show you is that when increasing the load of the applications, clearly at the beginning all the schemes are able to reach to keep pace with the application, but at some point we get to start getting saturated, and depending on which is the level of reliability we want to achieve, we can be able to saturate or to use more efficiently the available capacity. It's clear that if we want a very high reliability, so for instance less than 10% of the loss rate, we might not be able to get full saturation on the networks. While if we accept lower reliability, like 30% loss rate, we might have higher good output, so to be able to satisfy more applications. And this is what is interesting, that we also have compared with an offline scheme that is basically using some network utility maximization framework, but we observe that it's not working quite well. It's showing some inefficiency and degradation when the load is high. And the reason is that an offline scheme is using some static estimate of the link capacity, and is not able to deal with the variability of the conditions that we were observing in the real life. Then we have done something more sophisticated. So here the idea of the broker is that the application are not just asking for a single measurement from a single resource, but actually the applications are interested in a set of points. They want to measure a given phenomenon on a set of target points. And so we have in the area multiple sensor nodes. On these sensor nodes, we have multiple sensors. And so each target point can be monitored by different sensors, can be activated on different nodes. Our idea is basically to create a sort of digital twin for each of these target points. So each target points, we have a virtual sensory resources that basically decide which physical sensor to activate, how to collect the data from that physical sensor, and maintain the representations of the state of that for the target point. And then we create virtual applications resources. So we basically create synchronize these virtual application resources with the states of all the virtual sensing resources that are covering the target points that are of interest for a given application. What we have done, and the application specifies so the data type, the geographical scope, the update frequency ones. We have developed a mixed integer linear program problem formulations to decide which set of sensor resources to activate, a mapping between the activated sensor resources and emit applications, and which is the optimal probing rate of the broker for the activated sensors, which is the objective of the problem, is to maximize the number of emit applications, so to ensure a full coverage of the desired area, to prolong the network lifetime, to activate so only sensors where needed and when needed. So we have developed the prototype of these solutions. We have tested it in scenarios where we have sensors with different capabilities. We have the temperature, camera sensor, gas sensors. We have applications that are requesting different type of data with different number of points, with different frequency. And we compare with a solution where basically we have a node virtualization, so where the services are deployed directly on the device. So it's not allowing to have information reuse between different applications. And what we observe that when we increase the number of applications, quite soon the approach that doesn't have information reuse is getting saturated, so it's not able to admit more applications, where we are able to admit almost all the applications thanks to this caching and information reuse capabilities. We consume less energy, we are able to activate less resources, and most of all, we are also more fair with respect to the different applications. Because, for instance, the benchmark was giving preference to applications that were requesting just 1 point or a few points, while we are interested in admitting maximum number of applications. For in this case, all the applications have the same value, and so we are able to admit in a fair manner the different categories of applications. Then the last point I want to make on this is also we have investigated brokers that were able to brokers for every scenario. So where basically we have a static sensor networks that is augmented with an opportunistic mobile crowd sensing platforms. And so again, the point here is to be able to activate the sensors in order to limit the data redundancy and to increase the coverage of the networks. But the key point was to be privacy preserving, so not to use location information, but just only mobility profiles with the data broker. And very quickly, the idea was to basically to have the space divided in cells, and to be able to know which is the sojourn time of each device within each cell. Clearly, the static sensor have 100% sojourn time, so the mobile nodes will spend sometimes in one cell, then it will move to another cell. And the only thing that we were using in our framework was the percentage of time. So we don't know where the device is, we don't know when the device enters or leaves a given cell. We just know how much time it spends. And so basically this was a feasibility study, if you wish. So we were trying to understand if it's possible with such rough information on the mobility to do something smart, so to improve the coverage of the network. So also in this case, we developed an integer linear problem to select the optimal, to select the mobile sensor to use to extend the coverage of the static deployment. So this is the static deployment. Here we have also mobile nodes that are moving according to community-based mobility models. Again, we have different sensor types, we have different kind of applications, and we compare it against the static sensor networks, compare against the pure mobile crowd sensing solutions, and then with our combined systems. And we observe that the task coverage is much better when you are able to, even if you just have a very rough information on the mobility, you don't really need the location. Even with the rough information, you can do something better. And you basically reduce node activity, and you can reduce data redundancies with respect to a pure mobile crowd sensing. Now, with just the last 5 minutes that I have, I would very quickly want to show you some other results about data analytics in resource-constrained edge environments. So here again, what is my focus is on the data networking. So even when you want to do distributed analytics, the way you basically transmit the data in the edge networks is critical. It's critical to determine the efficiency of your distributed analytics, but it's also your accuracy. Because if you have a centralized machine learning approach, it's quite clear. You have all the data producer, the entire data set that's sending their data to the cloud, the entire data set is in the cloud. And you collect everything in a central location, you perform your learning task locally. But if you have a distributed machine learning, so you have your data sets that are located placed in multiple locations. So you have to compute partial models. You might refine your models by distributing your data sets, or by distributing your partial models. So basically you can have so-called federated learning, where you have the nodes that locally compute the models, and you send your partial models to an aggregators, and then you receive the global model. Or you then have a more decentralized learning, where you basically exchange data and partial model between the nodes. It's clear that with a distributed machine learning approach, you cannot reach the global accuracy that is reachable with a cloud-based solutions, because cloud-based will have the full data set to train its machine learning algorithms, but you can get very close. The problem is here, how costly is to reach a similar accuracy? So how much signaling traffic do you need in the networks? So basically we were evaluating different approaches, different strategies, and this is work that we have done, a colleague of mine have done, considering a simple linear classifier and applying some hypothesis transfer learning. So basically you have the partial models that are combined in an intelligent way in order to improve the accuracy of the target model. This is, in this scheme, is classical federated learning. You have the local partial models that are transmitted to a model collector that is making some aggregation of the models and sent back to the nodes. Or here we have basically the use of this transfer learning approach, where basically you have the models that are computed locally. All the models are exchanged to the other nodes. So there is a desynchronization phase, and with this transfer learning approach, the local model is improved. Then the improved model is again exchanged to all other nodes. So we have a second synchronization phase. And then all the nodes have their improved models, and they can aggregate these improved models using again majority voting or a consensus aggregation. So what is the key point here? Here you don't transfer data, you just transferred partial models. So how effective is from this approach? So we basically compared this approach using different data sets. One is about human activity recognitions, another one is images of handwritten digits. And just if you look to the accuracy, I just want to spend 30 seconds on these pictures. If you look to the accuracy, you have different data locations. So each location has a a fraction of the data set. So there are no locations with the full data set. You have the data set is split among the locations. So when you do the training with the local data, you have a variability on the quality of your models, because not all the data sets are the same. There are more data sets with higher quality than other data sets. Then you can do the first refinement, so the first synchronization with the transfer learning, and you improve the quality. And then you do the second refinement, you further improve the models, you get very close to the performance that you can get on the cloud, that is the green line. And you have saved a lot of bandwidth doing that, because what you have to do, if you look, you have to send to the cloud all the data, either the raw data or just the features of the data. While in this case, you transfer the models, so transfer the coefficients of the models, and you can able to save 50% up to 80% of the data by using a distributed learning approach with just a degradation of 5% with respect to the accuracy. But here we just transfer models. What about energy efficiency? So this is a different scenario, so where we basically transfer, we have the sensors, we transfer the data to basically mobile mules that are passing by the sensors. And in this scenario, so basically what we are assuming is that there is a deadline for the collection process, because for instance, the sensors are very tiny sensors, and you cannot store the data for a long period of time because they run out of memory. And so they have to transmit their collected data within a deadline. So either they transmit the data to the mule, or that at the end of closer to the deadline, they transmit the data to an edge server. So in the case of the mule, they can use short-range communication. To communicate with the edge server, they should use long-range communications, like for instance, narrowband IoT. Then mules and edge servers have, again, partial data sets, because the mules have the data sets they have collected from the single sensors, and they have to apply distributed learning to create a model. And if we look at just this important result, that even when just 3% of the data is on the edge, distributed learning is able to have a very close result to the cloud-based examples by dramatically decreasing the energy that you are consuming, because you are basically able to use short-range communications with the mules and not to use long-range communications to deliver the data to maybe a base stations using a narrowband IoT. So just to conclude, the key point here is that there is not a single answer on the question how to configure your distributed learning process. There are different models, so you can have a fully distributed model where they just exchange on the partial models. You can be fully centralized where you basically send all the data. You can have something in between where you have some collection point and you send partial data and partial models. The more basically collection point you have, the less data traffic you have to transmit. But the more signaling traffic you have, because you have to synchronize the models between these between the data collectors. And so how to provide the best trade-off between these two conflicting trends? This is a very open research questions, and we have some preliminary results on that unfortunately I don't think that I have time to show. Let me go to the conclusion of my talk. So in this talk, I will try to explain why data processing shall be proximal to data production. And I motivated this basically with the concept of data gravity. Then also I tried to elaborate on why we have these continuum resources and why it became so important to make resource orchestrations, taking into account that the resources are not just in the cloud, but there is a full continuum of resources very heterogeneous with each other. And this is bringing us many opportunities for research in the area of resource orchestration management, for instance, machine learning enhanced the congestion control, how to activate the sensors resources by using information that is available on the edge, how to have cooperations between different IoT service providers, so resource allocation in competitive market, IoT brokers, how to have place and federate brokers, taking into account that also brokers have resource limitations, how to perform this cooperative machine learning at the edge, and how to embed all these functionalities inside the emerging trends for edge computing, in particular in the MEC standard. So thank you for your attention, and let's conclude my talk. And sorry if I rushed up a little bit in the end. But
okay, thank you very much, Rafael, for this very rich presentation with numerous contributions. That was great. Indeed, we don't have much time, but let's take a few minutes for questions. Okay, we already have a question on the chat. Can you read it, Rafael? And if you can read, you can. I'll read to people on YouTube.
Okay. I'm sorry. Okay.
So the question comes from Evandro Macedo. So thank you for your really good presentation. Could you explain more about what you mean as resource-constrained edge environment? Isn't the edge environment supposed not to have constraints?
No. Basically, what we believe is that the edge can be everything. Can be your smart box, can be your Raspberry Pi, can be whatever, it can be an access point. So we have not to think about a huge data centers that have a kind of unlimited resources. What we are thinking about is a much more distributed environment where you have even every kind of resources that can be available, even small resources, have to be pulled together. So it's I think that one of the unique characteristics of the edge computing platform will be to take into account heterogeneity. It's not a uniform, homogeneous environment. It's a very dishomogeneous environment. And there will be always resources that are limited, so that can be saturated quite easily if you don't do allocation in a smart way. Just for doing, for instance, the closest edge servers or the less loaded edge servers, you can easily get in conditions where you get congestion and saturation of the resources. So the key point is that the heterogeneity of the environment is a key characteristic that we have to take into account.
Okay, so Evandro, thanks you for your answer. So it looks like he's happy with what you said. We have another question from Marty Andreoni. Guys, if you have a question, you can open your mic. Please go ahead, because it's more interesting for the audience. But if you cannot, I suppose you cannot, Marty, I'll relay the question to the speaker. So the question is, do you have an impression about energy efficiency of distributed learning versus federated learning?
Okay, that's a very interesting and fundamental question. Let's say, because for instance, when you talk about distributing the learning, you can even imagine that if you have a platform that you're using in an opportunistic way, our smartphones were not used. So the energy consumptions of the learning process is a key factor that we have to take into account. Now, it really depends on the problem. So, and depends on the technologies. What I was trying to show in my last contributions was basically that depends on what kind of technologies that you can use for communicating your data to the edge node. Because if you are going to use short range communications, it's clear that that will be very energy efficiency. But if you're using a cellular networks, although cellular communications are energy efficient, but you will definitely need more energy than what you would use if you use ZigBee, for instance. So it really depends on which is the node you have to reach for triggering the communications. And not always it's better to send the models instead of the data, because you can have a small data set that you are transferring. Now you can have models that have a huge number of features, and so you have a lot of different a lot of non-null coefficients in your models. So even the parser model that you are transferred can consume a lot of bandwidth. And furthermore, you have to think about that in federated learning, you just have one stage of model refinement, because you send the model to these aggregators, and the aggregators is basically combining the different models. When you do instead decentralized learning, you can have a multiple rounds of refinement, and this is the key to increase the quality of your solutions. But clearly, the more rounds you have, the more energy you consume in transferring the models. So there is a trade-off, and there is not a unique answer to these questions, because there are a lot of factors that you have to take into account, and the answer depends on the scenarios, on the kind of learning task that you want to implement, and also on the data set that you have. It's a balanced data set, it's an unbalanced data set.
Okay, thank you. Thank you, Rafael. There is one more question, because there is one. Okay, let's take this too. Okay, just because there was a question on YouTube, then we'll take yours. Okay.
Okay.
Okay, Otto. There is one question on YouTube, then Otto's question, and try to make short that, Rafael, because we have 2 minutes left before the next session. From YouTube, the question is from Jonathan Teixeira: how to deal with information security and data protection law, which can vary country to country in mobile crowd detection scenarios. And he congratulates you for the
in which kind of scenarios? In mobile? Sorry.
Mobile crowd detection.
Oh, mobile. It's clear that the best way to deal with the security concern is just to use the parser models and not to transfer the data. Because the way you can keep your data private is not to share the data. If you just share a model for your data, that is the best way you have to protect the security and the privacy of your data.
Good. You have a few congratulations from the YouTube folks. So Otto, we'll take yours, and before we stop, please go ahead.
So it was about privacy also. So you don't believe in the homomorphic encryption for a short time?
No, I'm not saying that you don't need cryptography at all. I'm saying that it's clearly that now is blockchain seems that it's going to solve all your security and privacy issues that we will have in a totally decentralized way. So, and blockchain is basically distributed systems with cryptography, and not more than this. I'm sure that there is a suite of tools that we have to use, but I think that's one of a very simple tool that we can apply, and is to keep your data separated from the data of the other users. And the distributed learning is definitely one of the approaches that is by design increasing the privacy of your data, because simply you don't exchange your data. Even you are not exchanging encrypted data. You simply don't exchange your data. So you exchange models of your data. Then we can ask, but even from the model of your data, we can understand some valuable and critical information on yourself. That's true. That is not a perfect solution, but it's better than exchanging your data.
Thank you.
Rafael, unfortunately, I think there were a few more questions, but unfortunately, to have to stop because the next session will start in 0 seconds.
No, I'm very sorry. It's my fault. I was too long.
That's fine.
Sorry.
You took your time to present to us your work. So if you are okay, people can make their questions on the chat. If you still have a few minutes to answer on the chat, or by email if you don't mind, because it was very interesting.
Send me all the questions that you want via email. I will reply.
Fantastic, Rafael. So again, thank you so much for your keynote. It was great. People are happy. You have a lot of thank you from the folks following your talk on the YouTube channel. Thank you again.
All. Thank you.
And now, Diogo, you are the general chair. So Igor, let us know if you have a break for a short coffee or not.
That's it. Let's wait for 5 minutes. Just a break of 5 minutes. That's okay for all?
Good. Thank you very much.
Thank you.
Hello, everybody. Welcome to the third and last technical session. This session is Next Generation Technologies. And the first paper, it will be presented by Evandro Macedo, and it's called Trust Aspect of Internet of Things in the Context of 5G and Beyond. Evandro, are you there?
Yes, I'm here.
Okay. You can start, please.
Hi, everyone. My name is Evandro. I'll be the presenter of our work entitled Trust Aspects of Internet of Things in the Context of 5G and Beyond. I'd like to start with a brief introduction to the current context of 5G around the world. Through this picture, we can notice that 5G has already started to be deployed worldwide with completely implemented 5G commercial networks in, for example, the USA, China, some countries in Europe, and also trials and research projects in many places, including in Brazil. With this coverage map, we can realize that 5G is already a reality for a bunch of places around the world. Nevertheless, what about this application? Can we imagine this scenario? Considering the IoT context, imagine that Alice is on a super fast train with her computer and she is controlling a drone that is flying really fast. How this communication would take place? Is 5G ready for that? Well, 5G presents really interesting KPIs, which stands for Key Performance Indicators, compared to the networks that we have nowadays. But they are still not sufficient for applications such as aerial, space, or underwater communication. Actually, IoT communication in such stringent scenarios is one of the main motivation for 6G research. So further challenges already take place in 5G, envisioning future applications, in particular those enabled by IoT. These challenges basically stand for 5G KPI improvements, which lead to 5G and beyond or 6G development. Some examples of improvements are the data rate that will jump from at most 20 gigabits per second to at most 1 terabit per second, including faster mobility support up to 1,000 kilometers per hour with reduced latency to nanoseconds, and also the use of sub-terahertz spectrum. However, considering the ecosystem of 6G and IoT, we should not forget the important and why not to say mandatory aspect of security that needs to be considered from the beginning of 6G and IoT development. 6G will interconnect a myriad of heterogeneous equipment with resource-constrained devices, needing to provide them with not only with ultra-reliable, but also with low latency connectivity. So it must have security by design. And an important security aspect that we highlight and consider here in our work is trust, in order to minimize the communication overhead and improve its security level. And so how to establish trust between devices during their communication? Well, an interesting characteristic of 6G is that it considers blockchain as one of its building blocks technologies, and it can help indeed to build trust between those devices. Just remembering that blockchain is a distributed ledger that is capable of providing an immutable and tamper-proof chain of blocks through some consensus protocol, for example, the proof of work or the proof of stake. So in our work, we propose a mathematical model for trust between IoT devices that is capable of capturing the network behavior of devices and translating it into a trust metric. We propose a trust model based on two components that are both high-level and low-level components that we will see more deeply in the next slides. We consider blockchain to store devices' identities using identity-based encryption that we'll see in more detail next slide, and also a relative entropy of the traffic or the cubic library divergence, and the temporal decay component. So let's see more details about this. To quickly introduce the identity-based encryption, it is a cryptographic scheme proposed by Shamir that makes use of identities to generate private and public keys. Originally, it is centralized in a server called PKG, which stands for Private Key Generator, that contains information about all entities in the system. So, for example, if Alice wants to send a message to Bob, first she collects public parameters, for example, Bob's email, and builds an encrypted message with Bob's public key. As Bob receives the encrypted message, he can decrypt using his private key obtained from PKG. So, what we propose in our work is to move the PKG to a distributed ledger, which leads to the blockchain motivation that we mentioned before. So the trust components are modeled as follows. The TR or the TRIJ of T is the trust metric we are looking for, which means the trust that the device I has in device J at time t. The high-level component here, given by BC of J and T, where J is a device and T is an instant in time, stands for a blockchain component that is responsible for providing an initial trust of a device in case of a communication between devices that don't know each other. The low-level components given by RE of X and T and TD of T, in which X is a random variable that represents the incoming traffic of device J, stands for a network level point of view that computes the relative entropy of the incoming traffic of a device, which is also known as the cubic library divergence, and also a temporal decay component that works like a timeout to reduce trust value after the end of communication. So the cubic library divergence is defined as the sum of each px of x times the log of px of x divided by qx of x for all x between 0 and c, where c here is the capacity of the transmission channel, and it is also the expected value in px of x of the log of px of x divided by qx of x. Or this is also called the relative entropy and we take the inverse of the divergence. So as the more distant are the distribution, the less we count to trust. So this is our model that we use to compute the trust metric. And okay, now let's consider the 6G IoT scenario in which Alice and Bob want to communicate and how our approach fits to it. So first Alice and consequently Bob, we will obtain an initial value from the high-level component, which means to check the reputation of the identity of Bob in blockchain. Then, given that both identities present a minimum level of trust, they can start communicating normally through the internet. As this communication happens, the low-level component takes place by adjusting the trust value according to the traffic behavior of the sender and the temporal decay when they stop communicating here. So in this scenario, we made an experimental evaluation to verify the efficacy of our approach in terms of the low-level component. First, we use a real data set that is composed by traffic traces from a smart campus environment, instrumented with a diversity of IoT devices, including cameras, lights, sensors, and health monitors. In the left plot here, we see traffic in bytes per second over time, where we slightly modified the traces by adding some spikes from 10,000 seconds and approximately 23,000 seconds to observe how our approach might behave. In the right plot, we see the trust metric in y-axis over time also, and we can observe that the trust value increases as soon as the traffic pattern begins to stabilize here. Then, when the first spike is reached, the trust value drops with different depths depending on the size of the window slide window. Sorry. Then, as the spike turns to be the new pattern in this period here, the trust is start to increase again. So this becomes the new pattern. These changes show how the operation, how is the operation of the low-level component and how it can capture the traffic changes by the relative entropy component. We also considered a synthetic data set with constant traffic pattern as the expected traffic or the ground truth of the traffic, and the periodic traffic that is the actually received traffic, like an anomalous traffic. In the left plot here, we also see the traffic in bytes per second over time, and is represented, the constant traffic is the triangle green curve here, and the actually received one is the squared orange curve that has this pattern. And in the right plot, we see the trust metric in the y-axis over time, and we can observe that it follows a similar pattern according to the changes in behavior, in the traffic and behavior, in which the trust value increases when the received traffic matches the expected one, while trust is penalized when the received traffic diverges from the expected. So these results help us to assure the effectiveness of our approach. So we wrap up by noticing the security importance in the context of 6G and IoT development. We developed a trust modeling in this context, considering high-level and low-level components. The low-level component showed its capability to capture traffic changes by penalizing or increasing trust accordingly. And we seek for future improvements to provide initial trust with a real blockchain, considering an edge computing, and also aim to evaluate the efficiency of our approach. So these are our contacts if you want more information about our work, and thank you very much.
Well, thank you, Evandro, for your presentation. And let's see if we have any questions. Okay, okay, Marcelo.
So, someone tried to make a question, Martin. I don't know who. Maybe Otto.
It's me.
Okay,
it's
go ahead, Otto.
No, it's me. It's Diogo.
Okay, sorry. Go ahead, Diogo.
Evandro, I have a question. In fact, you show your results as the trust evolves along the time, but I didn't see some results on an attack. If you have an attack, if you have something that disturbs the trust in your system, how does it react?
Thank you, Diogo, for your question and for the opportunity to present here. Actually, we consider the scenario in the example of the traffic traces that I used. Actually, it presents some attacks within, and to stress this behavior, to test our approach, we put that spikes to stress the like an attack behavior. So we actually test our approach in this attack scenario.
Okay, thank you.
Thank you.
If I may, so Evandro, thanks for the talk. My question was, we're thinking about the future, and you mentioned that you intend to do some future improvements of your work using blockchain. You put this in the last slide. What do you mean exactly by future improvements? What do you think are the next steps for as future improvements for your work?
That's great. The future improvements are real deployment, like a real employment for blockchain infrastructure, considering real data set coming from a blockchain implementation, and also application level information to, like, for example, to know what would be the ground truth that we expect for not only for the traffic, but also for the trust. If we have, for example, an application that is like a lamp, a smart lamp, that might have a periodic traffic. So this is the ground truth for this application. But if we have a camera, a video camera, we have a continuous traffic. So this is the ground truth for these applications. So we have different kinds of ground truth, and we only and we can only notice this with high-level information, and this is not covered by this work. It's out of the scope of this work. So it's the future improvements that we aim.
Okay, looks like you have a lot to do. There's a lot of work.
Yes,
okay.
yes.
Okay, good, great, thanks.
I
Thank
have
you
a
very much.
question. Can I ask the question?
Yes,
Okay, last
Professor.
one. Otto, go on.
Thank you for the talk, Evaldo. Very good
Thank
talk.
you.
You told about blockchain. You have a prototype that use a blockchain, and what was the blockchain that you have used?
Oh, this is a really interesting question because it is a work in progress. I searched for example, I don't know if you know this the Tezos blockchain that works with proof of stake instead of proof of work. We are aiming to apply this blockchain infrastructure. And actually, for this work, this current article, we just used synthetic results, like forecasting, like imagine how would be the answer from a blockchain, from a real blockchain. That is related to the previous question. So, one of the blockchain infrastructure is Tezos.
Okay, let me ask you if you will talk about the nanosecond of lattice. Do you think that a blockchain will be responsiveness with this lattice?
Yeah, this is we have to have in mind because we know that blockchain might be an overhead. It might imply an overhead, but we can work with different levels of blockchain, like different scales, like a local blockchain, for example, for a house or smart city, local smart city or neighborhood, and different levels of blockchain. So to the city, to the country, to the world. For example, I imagine that.
Okay, thank you.
Thank you, Professor Otto.
Okay, thank you, Evandro. Thanks for the audience for the questions. I think it's time to pass to the second presentation. Second presentation will be on the security and performance of proof-based consensus protocol, and it will be presented by Gabriel Revelo, Gustavo Camilo, Lucas Guimaraes, Lucas de Souza, y Professor Otto Carlos Duarte. Please, you can start.
Hello, everyone. I'm Gabriel, and I'm here to present the paper on the security and performance of proof-based consensus protocols. I'll be presenting it along my two friends, Mr. Gustavo and Mr. Lucas Ayran, who are also co-authors of this paper. So, in the past, researchers were trying to propose a system that would allow transferring money in a decentralized way. And this actually remained an open question in research for over 30 years until in 2008, Bitcoin was proposed by Satoshi Nakamoto. And in Bitcoin, Satoshi proposed two very important things. The first one was, of course, the blockchain. He proposed a new data structure that was organized into blocks, and in each block was linked to the previous block by the hash, thus creating an immutable blockchain. And the second thing he proposed was proof of work consensus. Proof of work consensus was a type of consensus that was different than any other ever proposed. We'll talk more on that later. And of course, since Bitcoin, many other cryptocurrencies emerged. First we had Bitcoin, then we had Bitcoin Cash, Litecoin, Ripple, Ethereum, and many, many others. And actually today we have over 7,000 cryptocurrencies that we know of. And these already account for $340 billion in market cap. However, cryptocurrencies is just one use case of the blockchain. Now we know that blockchains could be applied to other contexts and to protect other kind of digital assets. Digital currencies or cryptocurrencies are just one kind of application, which is on the right top side of this graph, but there are many others. And now it's more common to talk about blockchain-based systems. So cryptocurrency is a kind of blockchain-based system in which you transfer money, but there are many others. And with so many cryptocurrencies, so many applications, so many use cases, so many protocols, some questions arise. The first one is, how can we classify those protocols? So is there a way to put all those protocols into little boxes and check out their similarities, their differences, and how to apply them in each context? The second question is, how secure is each protocol? So if you're investing money on cryptocurrencies or in any other application, you want it to be as secure as possible. Third question, how efficient is each protocol? In many systems, you need to process a lot of transactions per second, and you need a lot of throughput, and we have to know which protocol will address that specific case. And the fourth question is, how scalable is each protocol? If you have a system that needs to attend to millions of users, which protocol should you use? The goal of this paper was to address those four questions. So on to the first question, how do we classify protocols? Basically, what we found out was that protocols can be classified into two main categories. The first one is quorum-based consensus. Quorum-based consensus, this is the image you should have in mind. You are a participant in a network, you grab the other participants, sit on the table, exchange messages, and reach a decision that will affect everyone, and hopefully everyone agrees. In a network of computers, that means exchanging messages and voting into a decision. So quorum-based consensus is based on voting rounds, and it provides very high efficiency because you can take decisions very fast. They're also usually more secure because you know the participants in your network, you know who you're dealing with. But on the downside, it needs, of course, participant identification. You need to know who are the guys in your committee, and it results in low scalability because in a network, if you have many participants and you have to exchange messages with all of them, you're going to flood your network. So it's not very scalable. This is why this kind of consensus is mostly implemented in private or federated blockchain-based systems. So a good example of this is a consortium of companies in which the companies do not fully trust each other, but they want to exchange some kind of digital assets. The second type of consensus, which was introduced by Satoshi in Bitcoin, is proof-based consensus. Proof-based consensus, what you should have in mind is this picture. There's no discussion, there's no agreement, there's just one rule. Whatever participant satisfies that rule and can prove it, he is the one who will propose the next block, and he is the one who takes the decision for the whole network. This type of consensus is based on irrefutable proofs, and so far it results in low efficiency. For example, Bitcoin only allows 7 transactions to occur per second. Proof-based consensus is usually less secure as well because you're dealing with public environments and you don't know who is participating in your network. But that, on the good side, provides anonymity. So anyone can join the network in an anonymous way, and there's no need for identifying participants. It also provides high scalability because you don't have to exchange messages. You just broadcast the proof and everyone has to accept it. And this is why it's mostly implemented in cryptocurrencies and public blockchain-based systems. Well, on this paper and throughout this presentation, we'll focus on proof-based consensus. We also have a technical report on quorum-based consensus, which you can check out if you're interested in our website. Okay, so on to the second question. I'll allow my friends Gustavo and Lucas to speak for me.
So the main idea of proof of work is to use hash functions to provide a puzzle that the nodes must solve to publish new blocks on the network. Hash function is a function that, if you have the output, is very hard, almost impossible, to guess the input. You have to do this in a brute force manner. Try all the inputs that gives the same output that you have. But if you have the input, it's very easy to just apply the function and calculate the hash. In the proof of work puzzle, it consists in to take the block information and announce that is a random number and combine these two information as input of a hash function. If the output have a certain number of zeros at the beginning, you solve the puzzle and broadcast the block to the network. And it's easy to verify because you send the information and the hash, so anyone in the network can verify the results. But since all the nodes on the network are trying to solve this puzzle independently, it can occur that more than one node solve the puzzle and propose two different solutions at the same time. This is what we call forks, and here we have an example. The purple block forms one branch of the fork and the black block forms the second one. And it's a big problem because you cannot guarantee that the overlap of these two branches will not lead to double spend transactions. So you have to choose one of these branches as the right one. And to do this, you basically apply the Longstein rule. The Longstein rule tells us to wait for the branch to become the longest one. When one of these branches becomes the longest one, you choose it as the right one. The purple blocks here are called alternate blocks because they are forgot by the network. The information is valid for the main states, the global state of the blockchain. They are discarded from the network. So usually, if you want to confirmate a transaction, you have to wait a certain number of blocks to be sure that your transaction will be not in an orphaned block and will not be discarded by the network. So usually in Bitcoin, you wait 6 blocks and it gives a high probability of your transaction will not be discarded. So in the proof of work security analysis, we can cite 3 main weaknesses. The first one is decentralization, because if you have a node that have more computational power than the others on the network, it can be solved the puzzle faster, and if it behaves maliciously, it can harm the network. In public networks, a big concern is a mining pool. That's a group of nodes that uses the power together to try to solve the puzzle faster. And if the mining pool starts to behave maliciously, it can harm the network. The second one is the need of communication between participants, because you only know that there is a new block or there is a new transaction when you receive messages on the network. So if you start to lose your message, you can be in a wrong state for a long period of time. The third one is the fork. It's basically the problem that I tell in the last slide, that you have two valid states and an attacker can explore this feature to start to trick the other nodes on the network to gain an advantage and start to do double spend attacks if he knows that the branch will become longest. So the proof of work attacks can be summarized in 3 main types of attacks. The first one is double spend attacks. It's when an attacker tries to use the same asset twice. The second one is the mining attacks. It's when an attacker has in some way much more power than the others on the network and try to harm the other nodes or gain an advantage. The third one is the network attacks. Is when the attacker tries to break the communication between the nodes and create invalid states or discard messages. So in a proof of work, you have a big environmental problem too, because when you try to solve the puzzle during the computations, it leads to energy consumption. And as the growth of the network, more energy are consumed.
So proof of stake comes as a more energy efficient alternative to proof of work. And the way that it works is that it chooses a consensus participant to propose the next block to be added in the blockchain. And the probability of being chosen as this consensus participant to add the next block is proportional to the stake that the participant owns in the network. So let's compare proof of work, proof of stake to see exactly how proof of stake works. And so on this library, on the left side, we have a proof of work scenario. On the right side, we have a proof of stake scenario. And as we saw before, the proof of work, the top miner has a higher computational power than the bottom miner. So the top miner has a higher probability of solving the cryptographic challenge and proposing the next block. That's not how it works in the proof of work, proof of stake consensus protocol. The way that it works in the proof of stake, when the top stakeholder has a higher stake than the bottom stakeholder, therefore he has a higher probability of being chosen to propose the next block. And as you can see by that the proof of stake does not require a high computational power, unlike the proof of work consensus protocol. And how exactly does this election work? This leader election works in proof of stake? Well, there are mainly two ways to elect a leader in proof of stake consensus protocol. The first one is to randomly select a coin, because when you randomly select a coin, whoever has more coins has a higher probability of being chosen as leader. And a way to do so is using the follow the Satoshi algorithm. And this algorithm receives a seed as an input and selects a coin as an output. And the coin owner of this selected coin is the elected leader and will propose the block in the next round. And this alternative is used by the Cardano cryptocurrency, which is one of the highest valued cryptocurrencies in market value right now. The other way to elect a leader is to hold an election. And in this election, you vote for whoever you want to propose the next block. And the votes are weighted according to the stake that the participant owns the network. This alternative is used by the EOS cryptocurrency, which is also a high value cryptocurrency. And as you can see, none of these two alternatives are expensive computationally. But that comes with a price. We have to remember the question that we want to answer here in the security part, which is how secure is this proof of stake consensus protocol? As we're about to see, the low computational cost to propose a block actually presents new security challenge that didn't exist in proof of work. And the first one is the nothing at stake problem. And this problem consists of participants validating multiple conflicting paths and a fork. And because there is no computational cost to validate or to propose the block, validators are always seeking to be rewarded, and the way to do so is to validate every possible path in the fork, and even if they are not legitimate. As we can see by our example here, an attacker creates a fork that the attacker block is represented by the red color in this slide. And as I'm a rational validator that wants to get rewarded, I will validate every possible block. And it might happen that the attacker blockchain goes faster than the main blockchain. And the longest chain will select this path. And the legitimate blocks that are on the other path are abandoned, are orphaned. And that makes it, that way the attacker can successfully perform a double spend attack. And that is the main problem in proof of stake blockchain. So how do we solve it? If that's the main problem, how can we solve this problem? Well, one alternative is to punish validators that validate conflicting paths. So you actually make the validator lose money, so it's not attractive to him to validate all possible paths. But that's not the only problem, even though it's the main problem in proof of stake protocol. That's not the only problem in proof of stake. The other big problem is the long branch attack. As we said before, there is no computational cost to propose blocks or to validate blocks. So an attacker can go back to the beginning of the blockchain and start to rewriting old blocks and eventually catching up to the main blockchain. How exactly does this work? We'll see it here as an example. We have the main blockchain right here, and the attacker goes back to the beginning of the blockchain and starts to rewriting the blockchain. And there is no cost to propose blockchain. He quickly catches up to the main blockchain. It might even go past the main blockchain. The longest chain will select his blockchain as the main blockchain. The attacker might perform in his blockchain a double span attack or erase a past transaction that was in the main blockchain that will be forfeited. And that is another big problem in proof of stake protocol. How do we solve it? How do we solve this problem? Well, a countermeasure that some blockchains implemented a checkpoint that restricts forking the blockchain. And this checkpoint actually sets a point that says up until that checkpoint, the blockchain is definitive, it cannot be changed. So if we implement a checkpoint after the block B1, for example, the attacker cannot fork in the zero because B0 and B1 cannot be changed. Can't fork before that point. That's one way to stop this sort of attack.
And besides proof of work and proof of stake, other protocols were proposed. Some of them tried to centralize consensus into some participants to improve efficiency. For example, delegated proof of stake and proof of authority. And the downsides of that is you can suffer from DDoS attacks onto the validators. And another very nice proposal by Intel was hardware-supported consensus. So in this kind of consensus, which is called proof of elapsed time, you need all the validators to have the same hardware, which supports hardware enclaves, and you can guarantee consensus by using the Intel hardware. But the main vulnerability is that we know today that we can compromise hardware enclaves in some manners. Okay, so we'll answer questions 3 and 4 simultaneously. So how efficient and scalable is each protocol? We did that by comparing different protocols regarding throughput and number of validators. So throughput represents efficiency and number of validators represents scalability. What we find out is that Bitcoin, which was the first cryptocurrency, achieved 7 transactions per second while having thousands of possible validators. The same happens with Ethereum, which is proof of work based as well, roughly the same problem. And proof of stake actually achieves more transactions per second, but it loses on the number of validators. And the same happens for other protocols. So what we find out here is that we kind of have a trade-off between throughput and validators. This is not a rule of the protocol, but so far, and the protocols that we analyzed, we found is this trade-off. And to conclude our work, we answered those 4 questions. We know regarding classification that protocols can be classified in either proof-based or quorum-based. Regarding security, proof-based consensus are more vulnerable than quorum-based consensus protocols. And proof of stake introduces new vulnerabilities. And the same might happen with any other protocol. Regarding efficiency and scalability, we know that proof of work is very expensive in computational power, and that proof of stake can be an energy efficient alternative to proof of work. But we observe a trade-off between efficiency and scalability, or throughput and number of validators. And this finishes our work. Thank you for your attention.
Okay, guys, thanks for your presentation. Let's see if we have some questions. Okay, Marcelo, go on, please.
Okay, hello, Gabriel. Very short one. You listed a number of attacks and issues that may encounter with blockchains, but in real blockchains today, what kind of attacks are being observed, if any, by the way?
Yeah, so for consensus protocols, it's basically proof of work in most cryptocurrencies today. So proof of work is at least in Bitcoin, is very secure. But those other cryptocurrencies that are becoming more famous, they're suffering attacks to the consensus protocols because their consensus protocols are less secure. So in real, if I would cite you example of an attack, Ethereum suffered an attack that split the cryptocurrency in 2. I think that was the biggest attack that a cryptocurrency ever suffered. But So all those protocols that we speak of in this presentation are mostly from smaller cryptocurrencies. So no real attack so far.
Okay. Thanks.
Okay, I have a more naive question. Besides these coins, what do you think we can use this proof-based consensus in what kind of applications?
Well, you can use it for any application that's supposed to be public, so anyone can join the network, and you can transfer digital assets. So, for example, proof-based consensus was used before to transfer documents in a global scale, and there's actually a proposal that I personally find very strange, but some guys propose proof of work to create kind of a document system that would allow you to build a country that was worldwide. I don't remember the name, but you for example, you could have a passport that's validated through the blockchain, and that uses proof of work.
Okay, thank you.
Can I complete the answer?
Yes, please.
There are some people that believes that the new internet will be a blockchain internet, that you can change the values instead of only data. They call this the internet of values. So there are people that say that the new internet is a blockchain internet. We don't know how this can happen and when, but there are some people that is studying this.
But do you think this could be tolerant to latency? Because I think that blockchain it's a bit could delay the transmission, right?
It's very difficult to answer this kind of question because I have never think about that we can transmit in the wireless gigabit and terabit, and they are the technology they succeed to do that. So if we can do this new internet with blockchain, I don't know yet, but if you have a lot of technology that will develop, it will be possible.
Okay,
So,
very interesting.
Yeah. So just to finish it, I don't think proof of work will fit that specific case, but there are many. Maybe other proof-based protocols that are more efficient may build that new internet of value.
Okay, I think it's very interesting discussion. I don't know if we have any other questions. Okay, so thanks guys. We will continue with the following presentation. The following presentation it's called Synthetic Relationship Approach to Construct Well-Informative Knowledge Graph Representation, and it will be presented by Nicolas Oliveira in collaboration with Diane Medeiros and Diogo Matos.
Hello guys, I'm Nicolas. Today I'm gonna make a quick presentation about the article called A Synthetic Relationship Approach to Construct a Well-Informative Knowledge Graphs Representation. I am one of the authors of this article, along with Diogo Matos and Diane Medeiros. We are from Mediacom and LabGen, both laboratories of Universidade Federal Fluminense. Starting with motivational aspects, I would like to emphasize a very useful statement which says the ability to store or access information is just as important as extracting it. We witnessed the validity of this statement when in the 90s we saw a migration of textual data from physical medium to web, the digital world. Today we face exponential increase of data, not only the quantity, but we are concerned about the quality of the storage. This concern refers to an inversely proportional relationship between data structuring and the complexity of analysis and processing. This relationship puts unstructured data sources such as PDF files, scientific article, patents as one of the challenges of the process of extracting, representing, and assessing the information. By the end of this year, 95% of the global data will come from infrastructure storage, and about 40% of global data will be accessed by cloud computing. All these challenges increase the demand of some semantic web application, such as ontology that we talk about in the next slide. But what is ontology? Ontology can be defined as a formal representation of knowledge domains. Roughly speaking, we say that ontology is a directed graph where nodes represent the concept and the relationships between this concept are represented by the edges. The process of creation or improvement of an ontology can be defined as ontology learning, where we use the minimal human intervention in the process. The whole process of ontology learning sees as a stack of texts. When we complete each of these stacks, we have partial outputs. The first output is the term when we extract words from the text. After we extracted the useful words, we establish concepts. When we establish relationships between these concepts, we have the relation, and after we generalize mathematically these relationships, we have the axioms. But what is our proposal? Here we want to express our proposal as a synthetical relationship approach based on natural language processing. The main goal of our approach is to generate knowledge taxonomies, which are lightweight ontology, a kind of ontology, where we establish hierarchical relationships between terms. The field of these taxonomies remains on cloud computing. Our proposal states as a hybrid approach where we identify noun phrases and we apply clustering algorithms. We use especially unrestricted data source, obviously cloud computing and documents. We use 82 specific papers published in Globecom last year, and the contribution of our proposal remains in build a well-informative representation of knowledge with 3/4 of original data and without any ground of truth labeling. As another contribution, we perform a quantity and a quality assessment. The architecture of our proposal is modular and admits the addition of new modules and is adaptable to documents from other areas. The first model of our architecture is the data collection model, where it emits several scientific documents in PDF, and we implement a systematic procedure composed by automatic conversion of 2 columns PDF to a plain text. And after these, we perform manual removal of non-textual elements, such as figures, expressions, mathematical expressions, references, and so on. After extracting the text from PDF file, we use informative text model to split the text into a set of sentences using period as a boundary criterion. After this, we implement a set of natural language processing in the NLP model. These techniques enable the manipulation and computational understanding of human language. To perform the natural language processing, we use 5 steps, which represent 5 techniques for cleaning and adjusting the textual data using Python library. The first step is the tokenization and discretization procedure that we transform a string, an entire sentence, into a list of tokens using the space character as the delimitator. After these, we perform punctuation and special character removal, where we remove any commas, hashtags, explanation marks, question marks, slashes, and so on. The third step is the token, a shallow parser, where we want to identify a specific syntactic structure. In this case, we want to identify sentences that are composed by noun phrases connected by verbs. The first step is the stop words removal, where you remove the most frequent terms of the text, such as articles, pronouns, prepositions. The last natural language processing technique is called lemmatization, a technique that produces inflecting derivative words to their lemma, the dictionary form, so we can eliminate possible variants and plural of a word. In the vectorization model, we transform words, elements with latent information, into numbers, elements that can be operated mathematically. The vectorization process in details can be done with a Python library called network_sheets, where we construct a graph composed by noun phrases as nodes and verbs as edges. After we construct this graph, we construct a adjacency matrix, a square matrix of size C, the number of nodes in the graph. This adjacency matrix is a binary matrix. The next model of our architecture is the dimensional reduction model, which implements latent semantic indexing, a technique indicated for sparse matrix. It transforms more than 6,000 dimensional matrix into more than 5,000, while preserving 99% of the features variance of the data. After the dimensional reduction, we use 3 unsupervised machine learning algorithms, commutations, the Bayesian hierarchical, to select the most central terms to compose the future taxonomy. After discovering the most central words, we introduce the outputs of the commutations and the Bayesian into a taxonomy formation model, we do that things your code algorithm already establish these taxonomy relationships between terms. The taxonomy formation process is made with 3 steps. The first step is the construction of a similarity graph between the most central words or terms. We use a symmetrical method based on normalized Google distance. The Google distance is a measurement that computes the distance between 2 terms, for example, fog computing and cloud computing. And considering the result, the individual search of each term on Google, and the search of the 2 terms at the same time on Google. In the evaluation of our proposal, we promote inter-methodological assessment, which we want to identify the quality of the clustering through the 2 interesting metrics, the dispersion between internal sample and separation between external samples. Here we have 3 metrics: the Davis-Baldwin score, the silhouette coefficient, and the Kalinske score. The first one, the higher quality of the clustering is measured with a value closer to 0, and the others 2, the high quality of the clusters is measured with a high score of the metric. So as we can see, the hierarchical algorithm has the most quality in both of 3 metrics, since it has the lowest value in Davis-Baldwin and the highest value in silhouette coefficient and Kalinske. In our inter-methodological assessment, we evaluate our proposal comparing with Casagrande methodology. Both methodologies are, the main goal is the taxonomy generation, but the state case is different. Casagrande use renewable energy state case, and our proposal use the cloud computing. The terms used in Casagrande are extracted from the analyzed paper, and they are the keywords of these papers. However, our proposal you try to extract the most central words in the text. We also apply NLP and machine learning, while Casagrande doesn't use it. We evaluate in a quantitative analysis, while Casagrande doesn't use this kind of analysis. The first comparison with Casagrande, we analyze the hits on Google derived by each branch of our proposal and Casagrande proposal. These hits on Google represent a popularity measure or a current state of maturity in the cloud computing field. As we can see in this box plot, we can see that our each branch of our proposal, countoids, the Bayesian and hierarchical, have maximum value higher than Casagrande, and mean value also higher than Casagrande. In the second comparison with Casagrande, we evaluate the coverage. The coverage is calculated with the sum of the verses of the set of keywords in each sentence, divided by the total number of keywords in the generates taxonomy. as we can also see here, the maximum value of our proposal are higher than Casagrande, and the mean value as well. In the conclusion, we present here a synthetic relationship approach constructing ontological structures. We implement an unstructured data source, which we use documents from the cloud computing field. We use several techniques of natural language processing, and we also efficiently use the application of unsupervised algorithm. In a intermethodological assessment, we evaluate the popularity and the coverage of our proposal in comparison to state of art, and we show that our proposal is 2.5 and 6 times higher than the state of art. And in intramethodological, we found that a single branch of our proposal, the branch called hierarchical, have the best quality of results. In our future work, we want to incorporate the number of citations given by the Google Scholar in the methodology. At last, we want to thank all the founding agencies, CNPq, CAPES, FAPESP, FAPESP, and RNP.
Okay. Thank you, Nicolas, for your presentation. Let's see if we have some questions. I do have a question. Did you test or evaluate the performance in time processing about these three algorithms that you present? Nicolas, are you there?
Yes, I am. Sorry, I was muted. Yes, we intend to do this in future work, but we don't evaluate the time consuming between our methodology and the state of art.
Yes, but my question was the three algorithms you used was scan, Kamedeutsch, and hierarchical.
Yeah, we use hierarchical, the Basecamp, and Kamedeutsch.
And which one do you think, or which one is your impression that was the better in time processing?
Time processing. There was the worst. Obviously, was the Basecamp, but we don't evaluate the time, but specifically the time, but in terms of evaluation, we use we preserve that Kamedeutsch was the best in terms of time.
Okay, thank you.
You're welcome.
Any other question? Okay, we don't have any other questions, so we are just on time.
Thank you.
Okay, Diogo, Igor, can we pass direct to the break?
Yes, we pass to the break right now, and we come back at 11:45.
Okay, thank you. This finished the third technical session. Thanks for your participation. Bye-bye.
Hi, everyone. Let's go and start the last keynote of our conference. Our keynote is Vinicius Sanger. He's a senior developer advocate at Amazon Web Services for Latin America and has worked with software development for the past 20 years. He's the founder of Global Code and the Developers Conference. Vinicius is considered a top 20 influencers in IoT development, having developed automation and robotic projects for cars, boats, houses, and many other things. Since 2017 at AWS, he has been working with IoT, serverless, machine learning, artificial intelligence, Alexa skills, and traveled around the world talking about innovation in AWS technology. I would like to thank you, Vinicius, for being available for this talk. And for now, we're going to start. Thank you very much for your talk.
Okay, good morning, everybody. Good afternoon, good night, maybe for you, good night, good evening, good evening, not good night. And so thanks a lot for this opportunity to show a little bit about IoT and things we are doing here in Brazil. And we are proudly deploying many things from Brazil to the globe. Producing hardware in Brazil is not something easy, but we are doing. And I'm very happy because today is Friday, because I'm talking about IoT that I love very much, and because I'm doing talks with my friends, invited by Pedro, who is my big friend in Rio de Janeiro, that I'm missing very much to travel there and to have moments with the very nice developers community there. And so I am a software developer the last 30 years, and the last 10 years I'm doing hardware projects. And since then we start connecting things, different things. I already connected boats, horses, houses, buildings, and many different things to the internet. And today I'm going to talk about ESP32 and how powerful is this, not microcontroller, we call it system on chip. Let me grab one here. I just forgot to grab one here to show you. That's the guy we are talking about. Very small, tiny, and very cheap also, because here in Brazil we can buy for like less than 10 bucks. And so this guy we have here, this silver stuff is the ESP32 itself. It has many ports where you can plug different sensors. You have Bluetooth, low energy connection, wireless Wi-Fi connection, and so we have a built-in antenna also. And it's very nice to do prototypes, for sure, that people are putting things in production with this guy as well. But you may, if the project is very, very serious and professional and industrial grade project, you may find something more professional, more robust. But from here, from this guy, you can start doing prototypes. You can do like robotics, home automation, or any other thing you would like to invent, to create. Okay, and the idea here is today is to show how powerful the do-it-yourself world can be these days, because you can really play with this guy using Arduino IDE, which is very simple. Like, I have a son, he is 14 years old, and he's an Arduino developer, proudly. So I used to teach kids here where I live here in Ubatuba, which is a ocean near the ocean city and near from Rio de Janeiro as well. But it's a very small city, a touristic city, and we don't have a very like rich people here. Like it's very simple city, you know. And even here, 10 years ago, we did a satellite with kids in a public school, and we developed a firmware using Arduino. So Arduino is very powerful because it can make it easy for anyone to create anything. But when you go to production, the things can get more serious. You need to do like updates over the air. And using Arduino, it can be tricky to manage thousands, hundreds of thousands of devices and update the firmware around the globe, you know, because these days we want to deploy globally our hardware. And so when you move from prototype to production, you can replace Arduino and you can start developing firmwares using FreeRTOS, which is a very professional operational system and real-time operational system. FreeRTOS means that real-time operational system, RTOS, we call here as FreeRTOS. And Amazon, like I think that 3 years ago, we just hired the FreeRTOS creator, and we start like sponsoring the project, and we did the Amazon FreeRTOS, which is like a sub project from FreeRTOS, but we have with Amazon FreeRTOS the security with very strong security for TLS 1.2, and we also have updates over the air features, so you can have like 2 partitions here, and then you can deploy the new firmware, and if it works, you can just change the partition that you are booting. So with Amazon FreeRTOS, you can use this kind of very cheap system-on-chip boards, development boards, do the prototype using Arduino IDE. That in the end of the day, if you are using Arduino IDE, behind Arduino IDE, it will be using FreeRTOS as well. So it's always FreeRTOS. But Amazon FreeRTOS, you can have a more professional security features. You can manage your devices better. So let's start playing with this guy here. So, but before doing that, I would like to introduce for some simple idea that Amazon and AWS did in the past, which is this guy here, called AWS IoT button, okay? Just to show you the IoT platform, the cloud platform at AWS. So think that you want to create a button, like an emergency button or something like Amazon did that retail. You have the Amazon Dash button, which was a project where you have buttons like this one, that you press the button, and then if you press the button, it will send a message to Amazon retail, and then you have like beer button. You could have like a Heineken button. And once you press the button, you could buy the beer just pressing one button, one single button. It's the real one-click shopping concept. So to make the experience for Amazon customers better, so they could buy anything there. Wiper, they could buy many different things. So let's see this guy working. Basically, this is a Wi-Fi button. If I press the button, it will send a message. This button is a generic one. It's a development button. It's not a Amazon retail button. So this is I could do anything with this button. Like if I press this button, it means that we are missing coffee. If I press this button, it means that my father fall down. And so he is in danger and he pressed the button and I need to check and I need to send someone to his house to see if he's okay or not. So we could do anything with this guy. So this button, we have a microcontroller here. We have security here. We have certificates here. We have a cryptographic keys here. We treat this button in the same way as we treat a server. So for us, security is not because it's just a button that we are using like not a strong security. So let's see how does it work. This button is connected to my Wi-Fi. And then if I press this button, it will send a message, a TCP IP message based on MQTT protocol. MQTT, for the ones that don't know about MQTT, is a lightweight protocol for IoT. It consumes much less battery than like HTTP, or if you do like IoT with REST, it's okay, but not for production, not for devices that are surviving on batteries. And so this is Wi-Fi button with battery, and it can rest for like 2,000 clicks. And if I press the button, it will send a message, an MQTT message with cryptography and security and everything to AWS IoT Cloud. And then I can react doing anything with this button. Just let me turn on something here that I forgot as well. So let's see. Now I'm going to share my screen. I believe that everything is okay with the transmission. If we have any issue, please send me any text on the chat. I'm looking at the chat here. So let's share my screen. Okay, here we go. So now I'm going to open my console and console at AWS, and I'm going to the IoT core. That's the basic, and that's the main service for IoT. And then I'm going to test. I'm going to click on IoT. I'm going to MQTT is a protocol based on publish subscribe, PubSub, like JMS for Java developers, and like it's based on queues. And then I can subscribe to a queue, to a topic on a queue. And then if I click the button and I have thousands of subscribers, all of them will receive the message. And the IoT core and our MQTT server, I don't like to call it server, but as MQTT broker, it will be taking care and managing the delivery process. So I'm going to subscribe this topic, and now I'm going to click the button. I don't know if here we have the camera and my screen as well, but I'm clicking the button right now. It will start blinking, and then if we have a green light, it means that it succeeds to send a message. It could connect to my Wi-Fi, and it could. We have both. Okay, thanks, Diane. We have both. It will send the message. It means that the message was successfully sent to IoT cloud, IoT's core. So let's see. I'm going to click the button, start blinking white, and then here we go. We have the serial number of my button, so you could identify which button is this one. We have the battery voltage, so beside the button sensor, actuator actually, we have also the battery voltage sensor. So you can like manage if the battery is too low, you can send a message, oh, the next, you need to replace this button in the next few days. And then we have the click type, single. Okay, I could do the double click, 1, 2, and let's see. Here we go, double click. And the long pressed one, boom. Let's see, long. So we have 3 types of clicking. This is a very simple project, but it's real. It's an IoT button. Sometimes when we work with IoT, we just think about complex stuff. So just to show you here, I'm going to move my camera a little bit, but actually what I have here in my demo table, let me configure a little bit better. We have some money, we have some boards, and, but the idea is that I'm going to click the button, and then you see that the light just turned on. So I have here the message from the button. It's coming through the IoT core to our IoT service at AWS Cloud. And then I have this robot with a Zigbee module, and this robot is receiving, is also subscribing beside my browser. The robot is also subscribing to the topic IoT button /plus. And then this robot, it has a function here that reacts. If I press the button, single click, it will send a Zigbee message to this guy, another guy here in the side that you see blinking, that is a board for automation. This guy here, look here. Okay, so you can see here, this is an home automation board that we produced 5 years ago. And then you can do anything, like we have a relay here reacting to the IoT button. Now I'm going to double click the button, 1, 2, and then it will turn off the light. So very basic stuff, but very nice to start introducing you to IoT services and IoT core and IoT and ESP devices, because you could do a button like this in minutes with the things I'm showing here. Actually, the ESP32, it's much more powerful than just managing a button, but you could do a product. I'm just saying that sometimes you can do simple stuff like a Wi-Fi button instead of having like very complex projects and things like that. So, okay. Now, let's start talking about the ESP32. And instead of using this guy here, and using wires, plug-in sensors, using protoboards, like in a Arduino style, I'm going to show you something new here. I'm going to show you what we are doing here from Brazil. This is a ESP32 board that we produced. So the idea is that you can produce your own board, your own IoT device from scratch, even from Brazil, which is not simple, which is not cheap, but in US, it's like the paradise for doing this kind of stuff. So here we have the same system on chip, as you can see, the silver stuff is the same thing, but we have accelerometer here, we have temperature, humidity, pressure, we have light sensor, and we have LCD display, we have a battery connector here. We are working on battery here, and this connector is a solar panel connector, so it's very nice to play. And in this way, we can start playing with IoT without having wires, protoboards, and it's much more easier if you are a software developer and you are not a hardware developer, but you want to start playing with IoT. That's the idea. This project is called Playground for IoT. And Playground for IoT is a board that our team here in Brazil, I work as developer advocate at AWS. So I work with, my team is the developer relations team. Our mission is to help you to succeed with your dream using open source technologies, using IoT technologies, and using AWS cloud, which is very innovative cloud. So you can do innovation much faster than managing servers in the cloud. So you can do IoT projects using the concept of serverless. You don't need to manage MQTT brokers and QTT servers. You can focus in your product, and you already have a lot to take care. When you do IoT, you have the I, that means internet, which is good. How good? Because we have different cloud providers. You have the serverless concept. But the problem is that when you are managing IoT projects, you have the T thing, the thing, right? And think about managing the thing. The thing, for me, is the new server. You don't need to manage servers. If you like, no problem. You can manage servers itself in your house, in your office, in the cloud. We have more than 100 different types of servers that you can rent, paying daily, paying monthly, paying yearly, no problem. But managing servers is not a good idea when you have IoT projects, because you need to manage things that are distributed servers around the world. So you have a lot of work already. So you should avoid having servers when you do IoT projects, so you can focus more on your thing than focusing on internet. So Playground for IoT is an open source project, an open source hardware project. You can produce this board. You can make money with this board. All the Eagle files, the files to produce the board are here. You have the list of the things you would need as well. You have the documentation, the technical resume. So it's based on ESP32, accelerometer, temperature, humidity, pressure, light, battery voltage sensor, solar panel sensors, and the most important thing, you have also some groove connectors here. You have 3 groove connectors that you can plug up to 200 different sensors, and you can extend the board plugging your own sensor. Okay, so to demonstrate, I'm going to use Arduino IDE. As I told you, we can use Arduino IDE to do the prototype. And then if the project succeed, you can move forward, and then you can use Amazon FreeRTOS to have a more professional and industrial grade project using ESP32. ESP32 is certified for Amazon FreeRTOS, but you have many different options, like more professional boards, and not boards, but system on chip and microcontrollers that are certified to work with Amazon FreeRTOS. Well, basically, when we have a microcontroller, we have pins, we have ports that we can plug our sensors. So here in our case at Playground for IoT, we have LEDs, 4 LEDs in the ports 18, 19, 13, and 14. And then we have 2 methods, 2 functions, basic functions in Arduino. For any Arduino, we don't call as firmware, we call as Arduino Sketch. In any Arduino Sketch, you are going to find it's mandatory to have the setup function, setup method, and also the loop function. So the name is very intuitive. The setup, it will run once it starts, it will run the setup, and then you can do anything you need to set up just once. And then since Arduino is not an operational system, it can have operational system behind, but we are not running multiple programs in our Arduino board. It's not the concept. We just run one program per time, one sketch per time. Your sketch can do more than one thing, but it will be in loop forever here. It will be doing the same thing forever. So what we are doing here, we are configuring our LEDs, our ports, digital ports 18, 19. We are giving a name here to make our code more readable. And then pin mode LED 1, output LED 2, LED 3, LED 4. Arduino, ESP32, I want to command, I want to write to this port. I want to communicate in a way that I can write to this port. And then I'm saying in the loop, digital write LED 1 high, or it could be 1, or it could be true. The 3 things will make the LED turn on. Okay, so I'm turning on the LED, making the port in a high voltage. I'm making the port in the voltage of 3 volts, so it will turn on the LED. And then I'm going to wait 1 second, so 1,000 milliseconds, and then I'm going to turn off the LED. So very basic program. This is the kind of hello world that we like to write when we are doing IoT. Actually, all the IoT professionals, what we do, we blink lights, bling, bling. I'm just kidding, because it's Friday. Okay, so let's upload the firmware. Here, I just have my ESP32. I did the setup, but if you are installing Arduino from Sketch to start playing with ESP32, you need to make a setup. You need to download the support, the ESP32 development kit to your Arduino IDE. Is very simple. You have many internet tutorials to follow and do this process. So, and my board is connected here in this port, which is actually a serial port. And then we are using the WCH chip for doing the communication, for doing the bridge between the USB and the serial communication. And it's working here. And then I'm just clicking in upload. And let's see. We should have some time here. It's uploading. Boom, 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 boom. Nice. And then we have here. Whoa! So we are blinking LEDs. Whoa! Nice. Okay, let's move forward. And let's see another example. This one is also a standalone example. I'm not showing anything connected now, just to introduce you to Arduino and to the basic concepts. And then here we have the same thing, but in the port number 23, I have a button. The same idea. So with this board, with the playground for IoT, I can do, we start thinking about producing the IoT button in Brazil. And then we thought that, oh, beside the button, we have many other ports that are free. Let's plug some sensors there. And then we did an IoT button with more stuff. But in the port number 23, I have the button. And then I'm saying that, oh, I want to enable the pull up. So in this way, the button will be on all the time. I'm saying that if I don't press the button, it will say, if I read the button without pressing the button, it will say, oh, it's on. And if I press the button, I'm going to interrupt the energy current, and then it will change to the zero state, to the false, to the low state. So what I'm doing here is that if I want to have my LEDs in the opposite way of my button. So if I press the button, it will turn on. If I release the button, it will turn off the LED. So let's see this guy working. Okay, so everything is okay. And then I can just press the button. Boom, 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 boom. You can see that in the loop method, I'm reading like in an insane pace the state of the thing. So it's very real time. Oh, look here, the response is, you don't have any delay. You can't feel any delay. The program is dedicated to listen to the button, and like forever, for the rest of his life, it will be listening to the button. And if someone press the button, it will turn on the LEDs. It's doing anything else. So that's the build of Arduino, or that's the build of real-time operational system. That's the build of bare metal development. You take care about everything. You take care about the timing. You take care about everything. So very nice. Now I'm going to move forward, and then what we are going to do is this guy here. Now the things will be starting getting connected. Okay, just to make sure that okay. So here we have a little bit more things. It's not the basic stuff. First of all, I'm including this guy called secrets.h. In this file, I have my certificates, my crypto, my certificate, my root authority certificate, my private key for cryptography, and then I have all the security embedded here. And then I have a Wi-Fi secure client, which is an Arduino library. Okay, so it's a standard Arduino library. Another good thing around Arduino is that you have many thousands of libraries to deal with thousands of sensors and actuators, GPS, cameras, sensors, gas sensors, a lot of gas sensors. And then I'm also including the MQTT client with that is also an Arduino library and Arduino JSON. So I can do JSON strings in a very JSON objects in a much easier way instead of managing the strings by yourself. And then I have a Wi-Fi library as well. So with these guys, I'm going to define that if I'm going to publish any data on IoT Core, AWS IoT Core, I'm going to publish in a queue called sensores, which is in Portuguese, like sensors. You just learned a little bit of Portuguese. And if I'm going to send something, I'm going to receive the messages. If I'm going to publish something from the board to the IoT cloud, it will be on the sensors queue. And if I have something coming from the cloud to my board, I'm going to subscribe. My board will be listening to a topic called command, and then I can receive the command and then turn on or turn off the light. So let's move forward. I have the Wi-Fi client and MQTT client. And then let's see our loop function. Our loop function, our setup and loop. Let's move to make it better. I'm going to move to the beginning of the code. Here we go. Setup. In our setup method, serial.begin in the bit rate that I want, okay? 9,600 bits per second. That's the speed, the connection, the serial connection speed. And then I'm going to set up my button, and then I'm going to call a function called connect AWS. Connect AWS. First of all, I'm going to set up my mode. I could be a router here. Okay, so I'm going to be a Wi-Fi client. I'm going to try to connect to my Wi-Fi. That's my credentials. It's very famous credentials. All my friends in Rio de Janeiro, they know that Surfing IoT. Vini always have a Surfing IoT network with him to do his demos with the password IoT, IoT, IoT. So if I'm near from you, I hope that we will be near soon. But if I'm near from you and you need internet and you find a Surfing IoT spot, and then just put IoT, IoT, IoT. That is Vini's IoT Wi-Fi. And then I'm going to send a message. Serial print line feed connecting to Wi-Fi. So if I listen to my serial port, I have here I have a serial monitor, and then I could listen to my device for debugging proposal or any other proposal. I just need to make sure that I have the baud rate in the right speed here to communicate with my board. Okay, and then let's back to the code. I'm going to wait until it can connect to the Wi-Fi. If I connect to the Wi-Fi, I'm going to set up the security with my certificate, my private key and everything, the certificate authority. To do that, I just need to go to our IoT service. I have here manage things, and then I just create a thing. Like if I have a new board, I just need to create a simple thing, and I can give a name, my ESP32 Friday. And then I can give a type. I can add this guy to a group. So if I want to do something like, I want to update all the devices that are based on Rio de Janeiro. So I can put this guy in a group called Rio de Janeiro, and I can put attributes to manage, and then you can do like SQL code to do updates over the air. So our IoT service is not just about managing IoT MQTT messages. We manage security, we manage updates, we manage we can like manage and monitor to see if the device has a different behavior, like, oh, this button just sent me the last year 10 messages per day, and why it's sending 10,000 of messages. And then our service can say, oh, that's a strange behavior. Let's put this guy, let's make this certificate invalid, so, and send a message to the administrator saying that we found something strange here. So you can defend your IoT cloud. And then if I click next, we can create one-click certificate creation, like when you are doing just one device, but you can manage in many different ways, create certificate, and then you can download your certificate, your public key, your private key, and your root certificate authority. And then with this, you can just open these guys, copy and paste the content here. I'm just showing the certificate authority here, no problem. But if I scroll down, I have my device certificate that I don't want to show you here because it's my security. But you just copy and paste the content of the certificate files to your Arduino sketch. So that's the way we have our keys. And we also have the IoT endpoint. What is this server, this IoT, this MQTT server? So I have here our AWS IoT. What is this string? Here we go. IoT endpoint. Here is the name of the server that I'm going to use. Again, to find that, I'm just come here in settings, and then it will show you which URL is your MQTT server behind. If I change the region, so here I'm North Virginia, US East 1. If I change the region, it will change the endpoint. Oh, Vini, if I have like if I'm deploying globally, how I can choose the right region to the right device if I have a multi-region architecture, because you want to do multi-region architecture. Like iRobot, they have more than 2 million robots all around the globe, and they want to use the IoT, the nearest IoT service for each robot. So you can have a region where you can do the onboarding, the device onboarding in a static region, and then this region can manage asking like, oh, where are you based? Or it can look from the IP source, and it can choose the right place. So sometimes we have a bootstrapping region, and then from this region we can send the device to the most appropriate region and with less latency. So we have many different architectures for doing that, and this is a separate talk, you know. So and then okay, so we already have connected to my Wi-Fi. We have the certificates. Then we are connecting to our IoT cloud in this endpoint. And then I'm saying, if I receive a message, I want to have a callback function. So client on message, if I receive a message on a command topic, okay, I will receive this message on the message handler, and then I'm going to start trying to connect to the AWS IoT cloud. And then, okay, and after doing the message saying that if I receive any message, go to this guy, to this function, I'm going to say that I want to subscribe the topic command, and everything okay, right? So now let's see what we are doing here. We are in our loop function. We are saying that if digital read 23, if someone presses the button, I want to publish the message. Let's see this guy in a more less sophisticated. I will explain this in a few minutes, but let's see the behavior. If I press the button, publish a message, and publish a message is a very simple function. Let's see here, I'm going to create a JSON object saying that the sensor A0 was pressed, or the state of the button, which should be 0, right? And then I'm going to publish the message to the sensor's topic, right? Which is behind this variable, okay? This constant is not a variable. And let's see the behavior of this sketch this way. So I'm going to upload. Now it will take more time because we have more libraries and we have more things to upload, to compile actually. Upload is the same time, is almost the same time. So writing, okay. Now it's working. Let's see. As I told you, I have the serial monitor here connecting to Wi-Fi, connecting to AWS IoT. IoT connected. Oh, good. Thanks, demo God. Doing live demos is not easy, especially when we are doing like webinars, you know. I'm happy that it's working. Now, I'm going to our console test, and I'm going to subscribe the topic that we call it as sensors. Perfect. So sensors. Subscribe the topic, and I'm going to press the button. Boom. Look at that. I have the message here. I just, Vinny, but you just press once. Crazy stuff. What's happening here? Look. Oops. Let's clear the console. I have more things. I'm subscribing to sensors. Just let me turn off my home automation system. Just a minute. Okay, good. So this way we can have just the message from the button. Right, perfect. Clear, and then again, look at that. I'm going to press very fast now. Ooh, I just press like click, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Man, I have here more than 20 messages. Crazy stuff. Look that I could, in one click, doing the loop function, just with one click, it read like 20 times. It's so fast that in a very small period of time, the button was pressed, it could read more than 20 times and send more than 20 messages to our cloud. It's very, very fast. So we need to do engineering. They call us engineering. In Brazil, we call us gambiarra. Gambiarra is a word that workaround. You learn more Portuguese today. Gambiarra is workaround. It's the popular name of workaround. But we call this a button debounce. Button debounce is a way that you can manage, because microcontroller, they are very fast. And but for us humans, I don't want to send a message, more than one message per second. Like, okay, if I press the button for more than 1 second, for me, it's okay to send more than one message. But if I just click, I want to send one message. What I'm doing here, I'm saying that if the time, so most of the boards, they have a real-time clock. If the time right now less than the last time that I send a message to the IoT core service is more than 1 second, then okay, publish the message. And then when I publish the message, I update the variable last time. So I have here last time, I initialize it with 0. And in the publish message, I publish the message and I update the last time I send the message with the time right now. So now we have a very basic concept of button debouncing. And then let's upload this guy again. Everything okay with the transmission, guys?
Yes.
Yeah. Okay, nice. Thank you. So we have some old stuff here happening. I have to put this variable before. Okay, let's see how. Okay, now it's okay. The year is 2020, and you still need to declare the variable before using. Oh my God. Okay, uploading. Nice, done, right? Perfect. And now let's check the behavior of our button. Clear. And then I will press the button. Okay. Again, guys, this is very fast. It's coming the message from Brazil to Virginia, come back to Brazil again in a very real-time way. Thanks for my internet provider here in Ubatuba, which is a fiber, very good one that makes me happy during these COVID times. Let's press again, and everything is working. Now let's see if I press. I never tried this. I'm going to press and keep it pressed. One. Now, look, 1 message per second. I'm just pressing and keep it pressed. 1 message per second because I did the debouncing this way. I could do a better debouncing algorithm to do like double click, long click, as I show in IoT button. But we have much more to show you here. And I don't want to spend the time talking about debouncing because debouncing is another talk, separate talk. And let's move forward. And now let's see the complete stuff. I'm going to use this guy here. Now it's much more code. Let's move this to this window. And now I'm going to use everything I have in my board. So here is the table of everything I have in my pins. I have the many code here with the AWS logo, the host name, the library for managing the accelerometer, the libraries for managing other sensors. So you can see here, each tab here is one different sensor, all in Portuguese. Inicializa acelerômetro, initialize accelerometer, and we have here the temperature and humidity, the LEDs, we have here the altitude, we have here updates over the air with Arduino, we have here the display, we have here, who is this guy, the light sensor, we have here the battery and the solar panel, and then we have here our secrets. So it's like the same thing with much more sensors plugged. Again, Vini, where I can buy this nice board? Now we are producing the beta version. In the future, I hope that you can buy. We have plans to produce in Seattle, in California, and in São Paulo, in Brazil. But if you don't have, for any reason, the availability in your country of this board, you can do it yourself. You can buy everything Adafruit, SparkFun. Here in Brazil, we use a lot of Mercado Livre, Amazon, and then you can buy the components and you can bundle the components in a protoboard or using wires, and then you can make your own playground for IoT. Let me upload this guy since we are almost in the end of this talk. Now it will take more time, and I would like to start saying thanks for everybody for watching us today. And let's wait here for compilation. Whoa, it's taking time. If we have any question, you can send, and I can answer. Meanwhile,
While we are waiting for compiling, there is a question in YouTube. Alexandre Kawamura asked, what does the AWS IoT platform use in the backend to process topics? A Kafka-style architecture?
no, we are using something similar to Mosquito. So we have an MQTT broker behind, and for IoT, we are using something more similar to Mosquito, which is an open source MQTT broker.
Thanks for that.
Okay, perfect. So here we go. Let's see which is the name of the topic. Playground. Now I changed it for playground/sensors. So that's nice. Thanks for your question, because like, Vini, I don't want to be locked into AWS cloud. Perfect. I understand you. And then you can use your own MQTT broker and you can have your own server. But as I told you, if you manage your own server, you need to manage the crypto, the security, you need to defend yourself, you need to manage the device onboarding yourself, which is not easy. So now let's subscribe to the right topic, playground/sensor or sensors. Subscribe, and then here we go. You can see time, humidity. Yes, I live very near from the ocean. This humidity just killed my guitar. Killed 2 times my guitar. It's terrible. And temperature, yes, it's hot here. The light sensor, I'm going to put my hand here, and we should have, okay. We should have the message up clear so it can scroll down automatically. So light is very much more, okay. So I just take it out my hand. Altitude, pressure, solar panel, battery voltage, the battery charge status, and then, so let me unplug from the cable and it keep working. Now we have the battery charge status, and then we have accelerometer. So if I move my board this way, we can see that the y-axis just changed. If I move this way, the x just changed. The x will change to 9 or 10. Let's see, 9, now 10, okay. So I'm playing, and then I could do anything. I could say that if I detect a fall down, I can send an emergency message. I can do like home brewing and monitor humidity of instruments of my guitar and things like that. So that's what I want to show you. But to finish, if you want to move forward, we have here this URL, and I don't know how I can share. Let me see if we have a public chat so I can share this URL with you. Here, guys, what we have here is the Same thing that I'm doing with the IoT button, using ESP32 and using Amazon FreeRTOS. So this is the part of the thing that we are doing Arduino, but here is the C code in a low level using Amazon FreeRTOS for, as I told you, industrial grade. So you can follow this tutorial and you can use your own ESP32 to start playing with Amazon FreeRTOS. So that's it. Stop sharing. Let's go back here.
Vini, for your talk, it was very interesting to see how to use ESP32 integrated with AWS. And I will open now for questions. If someone has some question, please ask here on WebEx or also in YouTube that I relate to Vini the answer the questions. For now, I still have a question about the IoT button that you presented just in the beginning of your talk. Is it already available to buy or in Amazon, this IoT button, or no, it's just for tests?
I think no. It was. It's not a project that we are continuing, okay? But I think that they still have. Let me check here. IoT button. They still have something. IoT button program. But look here. I'm not sharing, but it costs like $26. So it's very expensive. Like we are doing the playground for IoT, and the cost for us is $18 for everything that you have there. So the project, it was a good, like 4 years ago, the cost was $20 and it was okay, but these days it's deprecated project. It's much easier to produce yourself.
I got it. And when you say about this playground, the IoT playground that you showed us, the RTOS, is it based on ESP32, isn't it?
Yeah, we are using ESP32, yeah.
But is there any difference between the memory that's in this device of Amazon and the normal one that we buy in Mercado Libre or in place else? Is there any difference about memory or capacity, or is just the same ESP32?
Just the same ESP32. Node MCU, you can buy any Node MCU as I show here. And it is the same thing. We didn't extend memory or any other capacity for security. We could have here, what is good is that we could have like this guy and we could add a security element. So the crypto could be inside the security element instead being inside your code. So it could be like a more professional stuff to do. But no, we didn't. We just added the sensors and the actuators, and then you can do from scratch your own playground for IoT using protoboards, and you can buy everything that you have a playground for IoT here in Brazil. If you are watching from Brazil, you can buy all the components at Mercado Livre.
Oh, I got it. And
I think that Daiane, she has a question.
She has a question.
Can you hear me?
Yeah.
Thank you for the presentation, Vinicius. I have a quick question. I would like to know which services there are in the AWS showed, because you showed the server receiving the messages, right? I would like to know exactly if you have like some dashboard or something that could show us charts or something like this, more visual.
Oh yeah, we have many ways to do that. You can do your own like web app for doing a dashboard. We have many different services for doing analytics. We have IoT analytics. We have a AWS dashboard service that you could use. You could use CloudWatch for doing monitoring sensors as well. Many people do in a very simple way with CloudWatch. So let me just share my screen again, just to show you the one thing related to your question. So the good thing is that, like here, I have this act function. So I can create rules, and then I can say, like, if I receive a message, let me show you IoT surfboard. It will be the same. No, this is too complex. The button, I have a message, the button. Here you are going to understand. I am saying, if select everything from IoT button /plus. So if I receive a message from this topic, I would like to send the message to a function, and I would like to push a notification on SNS, and then I could send a SMS message. So here I could do any action, and I could like store the data in a DynamoDB. I could put on CloudWatch metric, and this way I could have a very simple dashboard. But there is one software that I really like very much for doing that is called Node-RED. With Node-RED, you can do very nice dashboards, and you can have like many flows, like saying, if the light is less than 1,000, then turn on the air conditioning or something like that. So Node-RED is an extra open source tool that you can use, but you need to manage a Node-RED server for doing that. But if you want something very simple, I would go with CloudWatch or our dashboard services. If you need something more complex, you can do yourself your web app for monitoring, and then you can have your browser connecting direct to your page, connecting direct to the IoT core services, and then you can do anything in your browser. So this is the most do-it-yourself way. So we have different levels of how you want to personalize and customize your dashboard.
Okay, thank you.
No problem.
Anyone has another question for Vinicius? Just to finish, I still have a lot of questions because it's a lot of things that you present, and it's very interesting. But you present us a sensor that is sending that data to the cloud. But in the case of an actuator, it should receive a message from the cloud. In this way, should I do a kind of pulling IoT device to the cloud, or the cloud can send message to the device?
No, MQTT libraries will take care about that. If you subscribe to a topic, you are going to keep listening to a TCP/IP port, and MQTT will take care about that. You don't need to keep checking if the message just arrived. You don't need to take care. So MQTT protocol and MQTT library in your firmware will take care about if I receive the message, then call this function. So I didn't show here, but we have working here. If I send a message from the IoT cloud, it will just call an Arduino function, and you just configure everything. You don't need to pull the TCP/IP port.
I got it. So the IoT device can subscribe to a topic as a subscriber itself. I got it.
Yeah.
More questions? John, still have a last question. We have time, John.
I promise it's quick.
No problem. If anyone have more questions after you can send me in the LinkedIn, Twitter, email. Feel free. I'm going to write my email here. Okay, go ahead, Diane.
My question is, we have a lot of ESP32 boards to choose from. So what would be your advice to choose one of them?
Okay. So if you want to have something similar to Playground for IoT, we have one called M5 Stick. It's available here in Brazil. So it's SP32 based, and it has a accelerometer, buttons, and actually we were inspired by this board to produce the Playground for IoT with more stuff. But if you want to do it yourself, you can buy any Node MCU kit. So if you go to Mercado Livre, you can put Node MCU kit, and then you have like 100 reais, and you can have the module, you can have some wires, some protoboard, and some sensors, and then you can start playing in a very easy way. But the M5 stick is it's a bundle already, like you have the sensors inside the board, like the same concept as I have here in Playground for IoT. If you don't want to put your hand, if you don't want to have your hands dirt with wires and protoboards, so it's a more high level development.
Okay, thank you.
All right.
Thank you, Vini, for your wonderful talk. It was very clear. It was very instructive for us. I guess people really like it. The audience in YouTube were about 20, 25 viewers at the same time, and we had 100 views along the presentation. So it was a good talk. Thank you very much for your presence here and for your talk.
All right. Thank you very much for the opportunity, and hope you have a great weekend, and hope you start playing with IoT. Take care, because you are going to get addicted with that. You start with this kind of small drugs, and then you will see in the end of the month, you have plenty of package arriving in your house. So take care.
I it happens.
Thank you very much, and thanks again for Pedro for doing the connection. Count on me on LinkedIn if you need any advice, or if you have any problem, or if you want to start playing, or if you need if you have any other question. Just go ahead on LinkedIn, on Twitter, my email, and reach me. I'm here to succeed, to make your dream come true.
Thank you very much.
All right. Bye-bye, guys.
I also thank Pedro for the link. Thank you.
Okay.
So for now, we're gonna finish our conference. It was a very nice conference. We had a lot of participants and a lot of keynotes that had brought us a lot of information and new things. And I would like to thank everybody for watching in YouTube and also here in WebEx. See you guys. Stay safe. Bye-bye.